and I'm going to share my screen. And first off, in the OneNote, today we're going to look at radical expressions and rational exponents. That homework P2 is due by the today. Homework P3 is due a week from today. Tentatively, there's going to be a coming quiz. I'm not sure if we will be ready for it on Thursday. If not, it will move till next Tuesday. It's going to be on exponents and radicals. And again, whether we have it Tuesday or Thursday is contingent on how far we get today. Before we get started with those radicals, we had left off looking at exponents. And as we were looking at exponents, we went through quite a few examples from the textbook and from my labs. And there you go. I was going to open my labs and ask if anybody had questions on any of those problems. And let me see if I can do that again. But while I'm messing around doing this, is there a reason for me to? Does anybody want to look at any of those back homework questions, either from the first section that involved working with expressions, or that second section that involved the P2 homework that involved exponents? You guys are all exponent pros and nobody has homework questions? If that's the case, then let's say that there'll definitely be an exponent quiz on Thursday, and I might pull off the radical questions and turn that into a separate radical quiz, or most of the radical questions. Nobody wants to look at any homework.
Am I allowed to ask a question about the quiz?
Sure.
So one of the answers on the quiz, I accidentally typed in a different answer in the answer instead of on my paper. So the answer on my paper was the correct one, and then the answer on the quiz was the incorrect one. Are you going to be able to check that, or because I typed it during
any work that was submitted before yesterday afternoon, I had gone through and graded already. And if you look in my labs, most of you will see that everybody who submitted work will see that your my labs grade has changed. And the reason I want you to submit that work in Blackboard is because those papers in Blackboard, I can write on as if I were actually grading a physical sheet of paper. And I can't hand them back to you, but you can still access them in Blackboard through the Blackboard grade book, I believe. You can click on it, something in the Blackboard grade book, and it will show you how I marked them. I have to say that previously, if I could tell that it was just something that somebody mistyped, I immediately went and gave almost full credit to. However, last semester I had problems with some people after they submitted their answers in my labs. They went through and did their work, and so their work gave them the my lab's correct answer and not the answer that they put in. And so what I'm doing this semester is giving you at least half credit for that.
Okay,
so
thank
you. Didn't quite get full credit, but you got at least half credit. And I apologize, but it's not that I don't trust you, but I know that there were some people in the past, and they felt perfectly fine doing that, submitting corrections instead of submitting the work that they did originally. And for people who did that, I couldn't really give them partial credit because that was, in retrospect, and I give you partial credit based on what you did before. So, but everybody, at some point in time, please do me a favor. And when you submit, if you submitted your work, please go into Blackboard and see if you can see those annotated papers, because I spend, a bit of time kind of going through and trying to find your mistakes and writing on them and all of that. And I know writing on them with the stylus digitally in Blackboard, sometimes my penmanship looks much worse than it normally does, but hopefully those comments are legible to you and it kind of points out where you went astray. And I guess I didn't mark on the papers how much partial credit I gave. That I did in the MyLabs grade book. I've got like 2 computers open, one with MyLabs and one with Blackboard when I grade things. So, but yeah. Did anybody want to look at any of those quiz questions or any homework questions?
Can we look at the quiz questions?
Sure. Which one? Or all of them?
All of them, if you could do that.
Sure. So, first one, evaluate the expression for x equals 3. I think everybody was real good at substituting the value for the variable. But then some people kind of messed up with their order of operations. Order of operations, first I do what's on the inside of the parentheses. So that gives me 3 plus 4 times 1 squared. There were a heck of a lot of people, and I don't know where it came from. This number in front of the parentheses is being multiplied by the parentheses. Make sure that you treat that as multiplication in between there. Next is exponents. 1 squared is 1. Then multiplication, 4 times 1 is 4. So here the final answer would be 7. That one okay?
Yes.
Then next, and I have to apologize. The questions come up randomly, so you all have the same questions, maybe with slightly different numbers and in a slightly different order. Next one again is a substitution. So here we're going to substitute 7 for x and -5 for y. Gives me the absolute value of, let's try that again. The absolute value of x is 7 plus y is -5. Now, there were a lot of people who did some really weird things and took absolute values of the pieces. Those absolute value bars, like we said in class, are symbols of grouping. So we have to simplify what's on the inside first. So 7 plus -5 is 2, and we're taking the absolute value of 2, which is 2. How's that one?
Yeah, that's good.
Okay, then next. Here again is an absolute value. We have -2 over the absolute value of -2. Well, the absolute value of -2 is +2, and so this quotient would be -1. There were a bunch of people who stopped here. Simplify, simplify, simplify. All right, if you stopped here, you got partial credit. But there were also a few people who forgot to take the absolute value. Be careful. And next, we have, and honestly, I have to say, I was a little surprised. There was somebody who typed me a message saying that they thought that this was a bad question and nobody would be able to interpret it. Let's go through and interpret it. It says we're taking a difference. We're subtracting. What are we taking the difference of? A product of 4 and a number. Product means multiply. So the product of 4 and a number is 4x. We're taking the difference between that and 3 times the number, which would be 3x. And so that first answer would be 4x minus 3x. And then the second, when we simplify it, is x. We'll put parentheses around there, which is perfectly fine. But we're taking the difference of the product and 3 times. So that product has to come first. Go ahead, I heard a question starting.
Yeah, I was just wondering, would there be questions like this on the test?
On the chapter test, yes.
Would it be like only one or like multiple?
You know what? I have to apologize. Again, this course was developed by the department, and I don't remember exactly how many, but as you go through and you do that problem set, that practice test that's going to count as a quiz grade, your test is going to be pretty similar to that. And so it'll give you a good idea of how many there are. All right?
All right, thank you.
You're welcome. So clearing that one. Next, use the order of operations to simplify the following. So we have 48. There are a lot of people that I think need glasses because a lot of people change that division into addition. That's division. 48 divided by 3 times the absolute value of 2 squared plus 3 squared. I'm writing this way too big. Over 7 plus 5 minus 8 squared. Numerator first, inside the parentheses, we do exponents. 2 squared is 4, 3 squared is 9. There were a couple of people who made computational errors there. And so inside there I have 13, and the absolute value of 13 is 13. That numerator becomes 48 divided by 3 times 3 times 13. Now with this, you have to be careful because remember with your order of operations, all that's left is multiplication and division, and that's all one step as it comes from left to right. And so 48 divided by 3 is 16 times 3 times 13. 16 times 3 is 48. 48 times 13 is, I have to apologize, I'm going to cheat and pull out my calculator because I don't want to do that one in my head. 624. Now, we're going to go through and do the denominator. In the denominator, exponents first. So that becomes 7 plus 5 minus 64. And again, you have to remember addition and subtraction are all one step as they come from left to right. So 7 plus 5 is 12 minus 64 gives me negative 52. And I'm going to cheat a little bit. And I'm going to try to do this division by hand instead. 13 goes into 52 4 times. And so my final answer there when I divide is negative 12. Saw careless arithmetic and saw people doing their order of operations wrong. Some people kind of divided 48 by 9 or something like that. And again, also some people copied wrong and that division became an addition. Be careful. This one better. Can I clear it?
Yes.
Then question number 6. Simplify the given algebraic expression. Again, what concerned me with this one was where we have that multiplication right in front of those parentheses. When we have that number right in front of those parentheses, that's being multiplied. So be careful with that. Another careless mistake that I saw was some people distributed the negative sign only to the first term. We have to distribute that to everything in the parentheses. And this then becomes 7 minus 4 times, and then we'd have 5 minus 4y plus 8. Then simplify what's in the parentheses. 5 plus 8 is 13. So that's 7 minus 4 times 13 minus 4y. We have to distribute that negative 4. So that gives me 7 minus 4 times 13 is 52. Minus times minus is plus 16y. And so then 7 minus 42 is negative 47. So you can write it as negative 47 plus 16y. or is 16y minus 47? Again, when you're simplifying things, you still have to follow your order of operations. You have to remember to distribute that negative sign. Some people, after they distributed that negative sign, multiplied by the 5. No, we're adding and subtracting these terms. And some people added the 4 instead of multiplying by the 4. Be careful. That one, all right.
Just writing in my notes. Can I have one more second?
Sure. Well, you have a second. I'm going to take, it's not a coffee break this morning, it's a tea break. And I'm always self-conscious when I have this headset on. I hope you don't hear me swallowing in your ears. I should take it off before I take a sip of tea. You all right now, hon?
Yep.
Okay. Then last but not least, again, simplify the algebraic expression. What we have here is 5 parentheses 5x plus 2, close parentheses, minus 4. Order of operations inside. Here I can't do anything inside, so I'm going to distribute, giving me 25x plus 10 minus 4. And then 10 minus 4 is 6, so final answer would be 25x plus 6. And I think I remember pretty much everybody getting that one right. So, feeling any better about these things, folks?
Yes.
Great. And other than the quiz, you folks are all right so far with that exponent homework. In which case, what we're going to do today is change gears a little bit, and we're going to start looking at radical expressions, which will lead us to rational exponents. If you remember last week when we were talking about exponents, we first defined things only for natural numbers as exponents. We were counting how many factors of counting numbers. Then we added 0 as an exponent and negatives as an exponent. Today, believe it or not, we're going to add rational numbers or fractions as exponents. But before we do that, we have to start looking at, I got to turn back to where we left off. Somebody likes just radicals. And we're going to focus on one type of radical first, and that's going to be a square root. And so we're going to define it to say that if A is equal to B squared, then B is the square root of A. When I write B equals the square root of A, B is called the root. The symbol is called the radical. And what's underneath the radical is called the radicand. And again, if we just have that simple radical symbol with nothing else, we're looking at that square root. So for example, I think everybody knows the square root of 4 is what? Anybody know the square root of 4?
2.
2. And that's because 4 is equal to 2 squared. I'm thinking, though, that the square root of 4 could also equal negative 2, because 4, positive 4, is also equal to negative 2 squared. And so this gives me the idea that every positive real number, 4 is a positive real number, and we're going to generalize from there, it's going to have 2 roots, a positive and a negative. I'm sorry, I have to rewrite that word roots for a minute. It's going to have 2 square roots. we'll find different later in the day. Two square roots, a positive and a negative, which kind of makes it a little bit ambiguous. And so if I just write the square root of a like that, radical a, that's going to represent what's called the principal or positive root. And if instead I want to get the negative root, I'll put the negative sign out in front. So if the negative sign is out in front, that's the negative root. And if we want to consider both, this is read as plus or minus. And we're going to use that when we want to consider both the positive and negative. So for example, if I just write the square root of 9, well, that just means the principal root or the positive root. So that'll be 3. Instead, if I put a negative sign in front of that radical, the negative root of 9 is negative 3. And if instead I put plus or minus the root of 9, I consider both 3 and negative 3, both of them. An interesting result that comes from all of this, if the radical without anything in front of it means just the positive root, we're going to be able to say that the square root of a squared is another way of defining the absolute value of a. And you might look at that and say, what? So let's look at an example. Let's say I want to take the square root of negative 5 quantity squared. Well, my order of operations says do what's inside the parentheses first. And negative 5 squared, negative 5 times negative 5 is positive 25. And so when I take the square root of positive 25, because there's no symbol in front, it's the principal root, and that gives me 5. And so do you see when I put in negative 5, I get a positive 5. And we can say that the absolute value of negative 5 is also 5. So when we take the square root of a quantity raised to an even power, it's like taking its positive root. Now, what if I ask, what's the square root of negative 36? Is there a number that I can square and get as an answer negative 36? Well, if I look at 6 squared, that's positive 36. If I look at negative 6 squared, that's also positive 36. And using our rules for signed numbers, when I multiply a sign by itself, the result is always positive. So that tells me that right now, this does not exist. Instead, we're going to say that it's not real. So negative numbers do not have a real square root. Probably, maybe in a couple weeks, a month, we'll start crossing that bridge and coming up with a different set of numbers, larger than our real numbers, that were created just so that we can answer a question like that. But right now, if you're asked to take the square root of a negative number, you're going to be able to say that it's not real. Some instances, the choice might be that it does not exist. Realize, though, that's only the case for square roots. In a few minutes, we'll define other roots where you can have a negative radicand. Any questions so far? To this point, is all of this vaguely familiar, something you've seen before, taking the square root of a number?
Yes, somewhat.
Okay, great. Then the next place we're going to go, is everybody okay if I turn the page?
Yep.
We're going to look at rules for radicals. And I'm going to go off on a tangent for a minute. At one point in time, way, way back, many, many years ago, I was a community organizer, and Rules for Radicals was a book written by an organizer, Saul Alinsky, and it was like our Bible. When I talk about Rules for Radicals, I am not referring to that book by Saul Alinsky. Instead, I'm referring to rules for radical expressions in math. We're going to find two that we're going to use right now. The first is the product rule. And this rule we're going to use in both directions. We're going to say that the square root of a times the square root of b is equal to the square root of a times b. Or because equality is a symmetric relationship, we can reverse that. So we can say that the square root of a times b is equal to the square root of a times the square root of b. And similar relationships hold with quotients. If I look at the quotient rule, we're going to say that the square root of a over b is equal to the square root of a over the square root of b. Or we'll say that the square root of a over the square root of b can be thought of the square root of a over b. And again, both those rules we're going to want to use different directions. Let's first start with a pretty cut and dry example that involves the product of two square roots. Let's say I have the square root of 3 times the square root of 27. And as I look at that, the square root of 3 is not rational. There isn't a number that I can square and get 3. It becomes a non-repeating decimal. And likewise, 27. But using this rule, I can look at that as the square root of 3 times 27. And 3 times 27 is 81. And the principal root of 81 is 9. And so what we're seeing here is that we can multiply two irrational numbers, and sometimes we'll get a rational answer. And sometimes if I'm taking the product of two radicals, and I can't take either root, if I take the product of the radicands, what's underneath, then I can take the root. In the same way, if I have the square root of 20 over the square root of 5, well, 20 is not a perfect square. That would be an irrational number, the square root of 20. 5 is not a perfect square, so the square root of 5 is an irrational number. But because they're both square roots, we can change that into the square root of 20 over 5. And 5 does go into 24 times, and I can take the root of 5 and get 2. And so do you see how those rules saying that if I'm multiplying two radicals, I can take the root of the product of their radicands, or if I'm dividing two radicals, I can take the root of the quotient of their radicands, allows us to evaluate expressions that might otherwise look irrational. we're going to use these rules in the opposite direction when we try to put a radical in simplest form. And we're going to say that a radical, or a square root to start with, is in simplest form. And we're going to have three criteria. We'll be looking at all three criteria today. First one is that the radicand has no perfect square factors. The second one is that the radicand cannot be a fraction. And then thirdly, we're going to say that if we have a rational expression, if we have a fraction, the denominator cannot be a radical. That's going to lead to something called rationalizing the denominator that we'll look at in a little bit. So the denominator cannot have a radical, cannot contain a radical. And so we're going to spend a little bit of time simplifying radicals. Before we do that, I find it's useful to make a list of perfect squares so we can determine whether we have a perfect square factor or not. Does everybody have all this down? Is it okay if I turn the page so I have a little bit more room to work?
Okay, I have a couple more. Okay, I have one more moment to finish these.
And again, if you're having a
Thank you.
hard time keeping up writing, you can, if you want to, just listen and pay attention, because besides putting that YouTube video, I'm also putting a PDF file of the written word in Blackboard. So if you just want to read the notes and you don't want to sit and listen to the whole class again, you don't want to take 2 hours in which to do it, there is a copy of just what's been written posted in Blackboard every day. Not every day, after every class. So, all right, you ready?
Yep.
Okay.
Thank you.
So let's look at our perfect squares. And again, with this idea of simplifying a radical, I almost think that it was a process that was easier for antique people like me than it is for folks like you, because back in the day, now I sound old, don't I? Back in the day, we had to memorize everything. And so we knew all of our multiplication facts, probably a little bit, with a little bit more depth than you guys do, because we weren't, I mean, the handout calculator didn't exist. And so we weren't using calculators. And so we needed to know our multiplication facts to be able to multiply and divide. So I think it's easier for somebody like of my generation to look at a radicand and simplify it, know what goes in evenly, than it is for you guys. But you know, if you have a chance to just brush up on those times tables, it's going to make these radicals easier for you, and it's also going to make factoring easier for you. But let's look at our perfect squares. Let's see how far you guys can go without a calculator. 1 squared is 1. 2 squared is, help.
4.
4, thank you. I thought you guys weren't talking to me today. 3 squared is,
9.
4 squared is,
16.
5 squared is,
25.
beautiful. 6 squared is,
36.
7 squared is, 49,
49.
8 squared is,
64,
9 squared is,
81,
10 squared is.
100,
How about 11? Do you guys know 11 squared?
120.
121. How about 12?
144.
144. Has anybody ever heard of 144 referred to as a gross? 12, a dozen is a gross. How about 13 squared?
169.
Anybody know 14 squared?
196.
15 squared? 225, and the list goes on. And so if I'm trying to simplify a radical, and let's start with a pretty simple example. For my example, I'm going to take the square root of 18. First thing I want to do is I want to find the largest perfect square factor of the radicand. And so let's see. 16 doesn't go in evenly, but 9 does. And so I'm going to express it as a product. Then I'm going to use that product rule. The square root of 9 times 2 is like the square root of 9 times the square root of 2. And I don't know if it's a helpful analogy or not, but at some point in time, I spent way too many years as a stay-at-home, not too many. I wouldn't give them up for the world. I spent quite a few years as a stay-at-home mom. And so when I see this, the square root of 9 times 2, it reminds me if you have 2 kids in one party hat. Never works. They always fight. So you give them each their own party hat. And then we're going to simplify what we can. Square root of 9 is 3, but the square root of 2 is the square root of 2. And so that's going to be my simplest form. So let's look at a couple more examples. Next example, let's say we want to simplify the square root of 128. Well, I'm looking at that long list of perfect squares. Can anybody see one that goes into 128 evenly? I'm waiting. If you're not sure, I go look at my list. First candidate is 121. That doesn't go in evenly. 100 doesn't go in evenly. I don't think 81 goes in evenly. But how about 64? Does 64 go into 128 evenly? Yeah, that's 64 times 2. And so I'll treat that as the square root of 64 times the square root of 2. The square root of 64 is 8. And so my final answer is 8 radical 2. And if you can pull out that largest perfect square, it makes your life easier. Some people might have said, okay, square root of 128. Well, I know that 4 goes into there 32 times. And so that's the square root of 4 times the square root of 32, which would be 2 square roots of 32. Oh, but wait a minute. 32 is 16 times 2. And so I could take that as 2 times the square root of 16 times the square root of 2, which would give me 2 times 4 times the square root of 2, which takes me to 8 radical 2. And I liken it to, if you want to, you can break it apart in little itty bitty pieces and dribs and drabs. But if you can find that largest perfect square that goes in, it just makes your life a lot easier. Now, sometimes we have variable factors. And so let's say I want to find the square root of x to the 6th. Well, I'm wondering, is there anything that I can square to get x to the 6th? Well, I know it's going to have a base of x, but I need to come up with an exponent. And does everybody remember that when we raise a power to a power, we multiply exponents? So I'm saying, what can I multiply by 2 to get 6? And that would be 3. And so the square root of x to the 6th is x to the 3rd. And because we're looking to say, what do we multiply by 2, does it make sense that a variable with an even exponent will be a perfect square? To find its root, we just half the exponent. Find the root, we keep the base, and divide the exponent by 2. You guys need me to hold off for a second?
Yes, please.
Ready? So if I want to find something like the square root of 121 x to the 18th, I'll take the square root of that coefficient, 121, and the square root of that variable part. 121 is a perfect square. Its root is 11. And because 18 is even, that's a perfect square. And to take its root, I'm going to think of taking that 18 and dividing it by 2 to get x to the 9. Instead, if I want to simplify, the square root of, let's say, 300 x to the 10th, well, this time 300 is not a perfect square. But if I go and look at, I'm going to scroll up a minute, those perfect squares, does anybody see a number that goes into 300 evenly? Hopefully, everybody recognizes that I can see that 300 as 100 times 3. And then that exponent on x is even, so that's a perfect square. This next line, I like to take the time to write out because I find that when people don't write it out, they have a tendency to make careless mistakes. When I take the time to put a square root over each factor, it helps me remember, okay, what's the square root of 100? Just 10. And it's just 10, there's no radical left. What's the square root of 3? That I can't take, so it's going to stay the square root of 3, and that factor stays under the radical. And then because that x has an even exponent, I can take its root, and it'll be x to the 5th. However, most often, we usually see something like that written as 10x to the 5th times the square root of 3. Usually everything that's outside the radical, those rational factors are written in front of the radical. The radical is at the end. And the reason I justify writing it like that is because if you have messy penmanship, sometimes it's like, oh, wait a minute, is that x to the fifth underneath or not? Kind of gets ambiguous. And so it's usually to put everything that comes out of the square root symbol in front of the square root symbol. So let's look at another one that's a little bit more challenging. Let's try to simplify the square root of 144 x to the ninth. So that's going to be the square root of 144 times the square root of x to the ninth. But over here, 9's odd. So x to the ninth is not a perfect square. And so if you have a variable with an odd exponent, under the radical, to get the closest perfect square factor, you just factor one of the variables out. What the heck do I mean by that? Do I have the square root of x to the ninth? Well, I can think of that as x to the eighth times x. I just factor one of those x's out. Now, why would I do that? Because this x to the eighth is the largest perfect square factor. So over there where I have the square root of 144 times the square root of x to the ninth, I'm going to think of that as the square root of 144 times the square root of x to the eighth times x, or the square root of 144 times the square root of x to the eighth times the square root of x, which will give me 12x to the fourth times the square root of x. And believe it or not, that's my simplest form. So, let's try another one of these before we look at doing operations other than multiplication and division with radicals, because this is a skill we need in order to do that. Everybody ready for one more? I'm going to shut up and ask you folks to simplify. Let's take the square root of 243 x squared y to the 7. And I'll give you a minute. So looking at this one, did anybody come up with a perfect square that goes into 243 evenly?
I got 81.
Beautiful, I like it. That's 81 times 3. X squared is a perfect square. And let's see, that y has an odd exponent. So y to the 7th will write as y to the 6th times y. How's that line for everybody? When we factor that number, we want to make sure that one of those are a perfect square. You can see which of your perfect squares go in evenly. Or another way is to, if you don't recognize them, is to look at this number and it looks pretty much like 3 goes in. When I divide out 3, what do I get? And when that other factor is a perfect square, I know I've got it now. So we'll take the square root of 81 times the square root of 3 times the square root of x squared times the square root of y to the 6th times the square root of y. Now, anything that's a perfect square, when I take its root, there'll be no radical left. So that'll give me 9 x to the 1st, y to the 3rd. And anything that's not a perfect square, those factors have to stay under the radical. So simplest form is 9xy cubed times the square root of 3y. How'd you guys do? It's a skill that takes a little bit of practice, and as you approach the homework, you'll be getting a lot of practice. In addition to those questions that just ask you to simplify a radical using the product rule, we're going to find that this is a skill that we're going to need in order to add and subtract radicals. So is everybody okay if I turn the page? To add and subtract radicals, I think that addition and subtraction is a very mean, nasty operation, because addition and subtraction, they're like, you can't join me unless you're just like me. And, you know, it's very discriminatory. In order to add and subtract radicals, we have to have like radicals. They have to be the same. And so in order to have like radicals, they have to have the same radicand. And we have to be taking the same root, which will eventually mean that they have the same index. But right now, we're just looking at square roots. In a few minutes, we'll look at other roots. So if one's a square root, the other has to be a square root, as opposed to if one is a cube root, the other would have to be a cube root, and so on. And when I add or subtract like radicals, it's kind of like combining like terms. So I'm going to say that I combine like radicals. So I add or subtract, depending on the operation given, the coefficients, and I keep the radical part the same. So let's say, for example, I have 7 times the square root of 5 plus 9 times the square root of 5. They're both radical expressions. And does everybody see that radical part is the same? And so just this once I'm going to write out the middle step. We're going to add those quantities in front of the radical and keep the radical part the same. Kind I'm just wanting to show you guys again that what we're doing is we're using that distributive property backwards. And so that's going to give me 16 radical 5. Instead, if I have something like 10 times the square root of 7x minus 6 times the square root of 7x, and I'm looking at the radical parts, and they're the same. Since they're the same, it's going to stay the same. And then looking at the numeric parts, 7 minus 6 will give me 4 radical 7x. Next example, I have 2 times the square root of 3 plus the square root of 2 plus 5 times the square root of 3. And again, what we have to remember is we can only combine like radicals. The radical parts have to be the same. So over here, I can combine the ones with the radical 3. I can take 2 radical, I'm sorry, I apologize, I miswrote there. I can take 2 radical 3 and add to it 5 radical 3. But then that radical 2, it's different. It can't be added. So here my final answer would be 7 radical 3 plus radical 2. And again, I'm fine if you can go from that first step to that last step. I just wanted to make sure that everybody was aware that when we did that, we were actually making use of our commutative and associative properties to get there. We had to change the order and regroup. Another example. What if I have the square root of 75 plus the square root of 48? Uh-oh. As I look at those right now, they're not like. However, we can't just back away from this problem and say that they're not like. Before we make that decision, we need to simplify each first. And so when I look at the square root of 75, can anybody think of a number that's a perfect square that goes into 75 evenly?
$25.
Beautiful. That's 25 times 3. Yesterday in my other section, I said whenever I look at numbers like 75 that are multiples of 25, I start thinking about quarters. And I think, 75 cents is 3 quarters, 25 times 3. And the person, one of the people in class responded to me, I don't worry about the change, I only count hundreds. Damn. But anyways, so that gives me the square root of 25 times the square root of 3, or 5 radical 3. Now, can anybody think of a perfect square that goes into 48 evenly? And I'm going to tell you, sometimes with these, I sort of try to work backwards to try to make my computation easy. Does everybody see that 3's left underneath? And so life will be easiest if 3 goes into 48. Does 3 go into 48? Yeah. How many times? Well, if you take 48 and divide it by 3, you get 16, and woohoo! It worked because 16 is a perfect square. Doesn't always work that way, but if you're not sure what goes in there evenly, try taking that radicand and dividing it into the other one. So that gives me 5 radical 3 plus 4 radical 3. Now they're like, and I can add them, and my final answer is 9 radical 3. And having seen that one done out, I'm going to ask you folks to simplify And I'm going to give you 3 radical 8 minus the square root of 32 plus 3 times the square root of 72 minus the square root of 75. You're going to have to simplify each of those radicals and then decide which ones you can combine. And I'm going to give everybody a minute to try to do that. Okay, are you guys ready to go over, or should I give you another minute? Need more time?
Yeah, can I get another minute, please?
Sure. You guys ready?
Yep.
Okay. So the square root of 8, I think we can simplify that. Did everybody recognize 8 as 4 times 2? So that gives me 3 times the square root of 4 times the square root of 2. Or 3 times, let's see, that square root of 4 is just 2. So that becomes 6 radical 2. Everybody get there with that one? Then, using that trick, 32 is even. Let's see what I get when I divide out 2. And so that gives me 16 times 2. And 16 is a perfect square. And so that becomes minus 4 radical 2. Next one's also even. So let's see, if I take 2, factor 2 out of 72, I get 36. Oh, great, that's also a perfect square. So I'll take 3 times the square root of 36 times the square root of 2, gives me 3 times 6 times the square root of 2, or I'm adding 18 square roots of 2. Now, sadly, 75 is odd, so I can take out that factor of 2, but I think we already said that 75 factors into 25 times 3, so that would be minus the square root of 25 times the square root of 3, or minus 5 square roots of 3. So first question, how did I do? Did I get the same simplified terms that you got? If so, now the like ones, they'll go together. Working with the coefficients, I apologize, I skipped a step, they'll go together, so I'll still have a radical 2 left. Working with the coefficients, 6 minus 4 is 2, 2 plus 18 is 20. And then that last one doesn't just disappear, it's just that I can't combine it. So I'll be left with 20 radical 2 minus 5 radical 3. Did you get there, folks?
Not exactly.
Well, if you didn't get there, does that make sense?
Yes.
Great. So that's how we're going to add and subtract. Next place we're going to go are rational expressions. And with rational expressions, we're going to have to remember that if something is in simplest form, it means that I cannot have a fraction in the radicand. And I cannot have a radical in the denominator. So if I look at something like the square root of 1/2, yikes, my radicand is a fraction. That won't work. So I'm going to think of that as the square root of 1 over the square root of 2. See, the square root of 1 is just 1 over the square root of 2. But yikes, there's still a radical in the denominator. And so what we're going to do is a process that's called rationalizing the denominator. We're going to see there's 2 different types of problems that we need to work with. First case we're going to look at is if there's just a single radical term. which is what we've got here. Just one term in the denominator and it's a radical. And so what we're going to have to do is we're going to have to multiply both numerator and denominator by that radical in the denominator. And most people find it easiest if they multiply it by that same radical. Sometimes, though, it's easier to multiply by a radical that makes a perfect square radicand, or a radical, and we'll look at that in a minute, that makes a perfect square radicand. So let me wait a minute. Let me know when I can carry on. Guys all caught up? What does all that mean? I have this radical 2 in the denominator. That's an irrational number. I always want a rational number in the denominator. So since it's radical 2, I'm going to multiply by radical 2. But because it's a fraction, I don't want to change what it equals, just what it looks like. And so do you see that if I multiply both the numerator and denominator by the same thing, I'm really only multiplying by the number 1. It's a funny looking number 1, but it's just 1, so it won't change the value. So here 1 times radical 2 is radical 2. Radical 2 times radical 2 is radical 4. And now I can simplify that into radical 2 over 2. And this is considered simplified because the denominator no longer has a radical. Again, in terms of why is that so important? It was very important back in ancient times when we had to simplify things by hand. The long division that you would have to do to simplify a fraction like this was terrifying, as opposed to the long division that you did to simplify a fraction like this was much easier. So it kind of goes back to ancient times and pre-calculator days, but it's still the norm. So another example, let's say I have the square root of 2/3. Got a fraction underneath. I don't want that, so I'll take the square root of the numerator times the square root of the denominator. I still have that radical in the denominator, it's radical 3. So I'm going to multiply it by radical 3. Whatever I multiply the denominator by, I have to multiply the numerator by. Anything over itself equals 1, so I'm just multiplying by 1. Radical 2 times radical 3 gives me radical 6. Radical 3 times radical 3, I'm going to get a little bit lazy here. Is everybody all right? Radical 3 times radical 3, when I multiply a radical by itself, then I just get the radicand. That would give me the square root of 9, which is 3. And this is simplifying. Can't go any further because one's underneath a radical and one is not. They don't mix. This is considered simplified, though, because there is no square root left in the denominator. Any questions on that one? Next one, then I want to do 2 ways. One, the way we've been working at them, and the other using that, like, sometimes, though, you might want to multiply by something else that we would put in the parentheses up here. If I have 2 over the square root of 18, well, I have the square root of 18 in the denominator. I'll multiply both numerator and denominator by the square root of 18. Numerator, I'll get 2 radical 18. Denominator, I'll get radical 18 squared, which is just 18. Let's see, I can simplify the fraction. 2 over 18 is 9, so that's radical 18 over 9. But that square root is not in simplest form. It's got a perfect square factor. I can think of that 18 as 9 times 2. So when I take the square root of 9 times the square root of 2 over 9, let's scooch this over a little bit. That gives me 3 radical 2 over 9. And is everybody all right? I can reduce that fraction 3 over 9 to get radical 2 over 3. And so this would be simplest form. After I rationalized the denominator, I had to simplify my fraction and simplify that radical that was left in the numerator. Instead, sometimes it's quicker if I can look at that 18 and say, okay, wait a minute. Doesn't 18, I'm going to backtrack for a second, doesn't 18 go evenly into one of my perfect squares? Doesn't 18 go evenly into 36? And so I can take numerator and denominator and multiply them by radical 2, which would give me 2 radical 2 over the square root of 36, which would give me 2 radical 2 over 6. And then that 2 over 6 would reduce to 9. Oops, I'm sorry. My hand is writing what's in my head and not what I'm trying to say. My radical 2 over 6 would reduce to a third. And so if you don't see anything else, you can always multiply the radical by itself. But realize you have to simplify. Sometimes, though, there's something smaller that you can multiply by to get that perfect square under the radical in the denominator. And so if there's just a single radical in my denominator, I'm going to multiply numerator and denominator by that radical or by a radical that makes it a perfect square. It gets a little bit dicier. Can I turn the page and not lose anybody?
I have a question.
Sure not.
How did the 18 in the denominator turn to 9?
Oh, I took the fraction 2 over 18.
Oh, okay, thank you.
Okay, thank you for asking. It wasn't magic. And amazingly, this time it wasn't a penmanship mistake. Whoops. Okay. If that's all right, then, what happens if you have 2 terms in the denominator? For example, what if I have 5 over the square root of 3 plus 1? I'm going to do it wrong for a second, because some people say, okay, there's a square root of 3, so I'll multiply top and bottom by the square root of 3. Top 5 square roots of 3, that's fine. But do you notice in the denominator, we'd end up with the square root of 3 times the square root of 3 plus 1, and we have to distribute. As that would give me 5 square roots of 3 over radical 3 times radical 3 is 3, plus radical 3 times 1 is radical 3. And so that didn't help me at all. There's still a radical left. So if you have 2 terms in the denominator, we have to define something that's called a conjugate. And the conjugate of A plus B is A minus B. My terms stay the same, but I take that opposite operation in the middle. And that's important because, can anybody remember, I know we haven't really multiplied binomials yet, but can anybody remember at all in a previous algebra class taking a product, multiplying something like A plus B times A minus B?
The FOIL method.
Sure. And so if I use that FOIL method, first, A times A is A squared. Outer, A times minus B is minus AB. Inner, B times A is positive AB. Last, B times minus B is minus B squared. Now these two are like terms, and minus 1 plus 1 is 0. So I'm left with A squared minus B squared. Does everybody remembering that shortcut? That if I take the product of the sum and difference, I get the difference of the squares, A squared minus B squared. And so what happens if I look at something like 7 plus the square root of 2, its conjugate is 7 minus the square root of 2. And the product, well, if I take 7 plus the square root of 2 times 7 minus the square root of 2, by what we just did, A is 7, so that would be 7 squared. B is radical 2, I apologize, I miswrote here, minus radical 2 squared, which gives me 49 minus 2, or 47, and there's no radical left. So, going back to that problem we put at the top of the page, which was 5 over radical 3 plus 1, to rationalize the denominator, if there are two terms. And again, that same example, 5 over radical 3 plus 1. We're going to multiply both the numerator and denominator by the conjugate of the denominator. So, what does that mean? If I have 5 over radical 3 plus 1, I want to multiply the numerator and denominator by the same thing. To find the conjugate of radical 3 plus 1, it'll have that radical 3, it'll have that 1, but it'll have the opposite sign in the middle, radical 3 minus 1. And again, whatever I multiply the denominator by, I've got to do exactly the same thing in the numerator. Let's look at the denominator first. Because these are conjugate pairs, we can be lazy and not FOIL it out. It becomes the first one squared minus the second one squared, or 3 minus 1, and my denominator is 2. Yay, it no longer has a radical. But in order to multiply the numerator out, because I've got multiplication in front of parentheses. Is everybody all right? I have to distribute in the numerator. So that gives me 5 radical 3 minus 5. And so my simplified answer is 5 radical 3 minus 5 over that 2. And again, it's considered simplified because there is no longer a radical in the denominator. Let's try another one. This time, let's check this thing full of radicals. Let's take the square root of 7 over the square root of 3 minus the square root of 2. Wow, that's a fun one. We have 2 radicals in there, in the denominator. They're not like, I can't combine them. And so we've got to find what's the conjugate. Find the conjugate, we'll keep those 2 terms, radical 3, radical 2, and because this is a minus, we're going to do the opposite operation to get that conjugate, so that'll be a plus. And again, whatever I multiply the denominator by, I have to multiply the numerator by the same thing, because by multiplying numerator and denominator by the same thing, this fraction, because numerator and denominator are the same, just equals 1. So not changing what my original fraction was equal to, just what it looks like. In the denominator, because they're conjugates, I'll get the first one squared minus the second one squared. So my denominator will be 3 minus 2, which is 1. I apologize. I wish I could work across, but I'm writing too big. So I'm going to have to work down on here. Now, let's find out what our numerator is. We'll have radical 7 times radical 3 plus radical 2. We have to distribute. So that'll be radical 7 times radical 3 plus radical 7 times radical 2, or the square root of 21 plus the square root of 14. And we don't really need to show that 1 in the denominator, so our final answer is the square root of 21 plus the square root of 14. And while I know both of those numbers can be factored, 21 and 14, when I factor them, there will be no perfect square factors, so I can't simplify that anymore. And so this would be my simplest form. So before we start looking at other radicals, I'm going to do one more, but actually I'm not going to do one more. You guys are going to do one more. Let's have you try 15 over 3 plus the square root of 17. And please go ahead and rationalize that denominator for me.
Is it okay to get negative, repeating numbers on this?
Say that again?
Would there be any repeating numbers on this by any chance?
We're going to leave things in radical form, and so you shouldn't worry about changing them into a decimal.
Okay.
So are we ready to go over yet or no? Does anybody need an extra minute or are we good?
I can use extra minute. Is that okay?
Yep, that's perfectly fine. And I
Okay,
hate to
thank
say this, I'm rude and I check my email
No,
all
you're okay.
but I give you
You're
guys
okay.
time because I'm not a patient person. So
Yeah.
I don't wait well, and I wish I could. Actually, there's probably some software out there where you guys can all write on a whiteboard and I can see what you're doing. But in that way, you're not getting it down in your notes. So I feel bad. I like to look over shoulders when I'm in a classroom. But I guess
You're
even
okay.
if you're on campus, I couldn't look over shoulders because then I wouldn't be socially distancing. So someday
All
life
right.
is back to normal.
Okay, thank you.
Let me know when you're ready. Well, let me know when you're ready. Ready?
Yep.
Because there's two terms in the denominator. I'm going to keep those two terms, 3 and radical 17. But I'm going to take the conjugate because this one's addition, the conjugate is subtraction. And whatever I multiply the denominator by, I multiply the numerator by. Because they're conjugate pairs in the denominator, I will always get the first term squared minus the second term squared. So my denominator will be 9 minus 17 or negative 8. In my numerator, I have to distribute. So distributing, I'll have 15 times 3 minus 15 times radical 17, which gives me 45 minus 15 radical 17. And that's it. And that, believe it or not, is considered simplified form. So all that we've been working with to this point are square roots. In the next 10 minutes, I want to just define other radicals. Before I define other radicals, I want to go to the first page of the notes and give you a heads up in homework P3. We will have covered questions 1 through 19. If you're brave, you can go past question 19. But past question 19 deals with those fractional exponents. And as much as I wanted to do them today, because they're great fun, we just haven't got there yet. So, going back to the end, let's look at other roots. And so we said the square root of a equals b if a is b squared, and that's our square root. For other roots, we're going to draw that radical. But over here, kind of in the check mark of the radical, you're going to see a superscript number. And we're going to talk about the nth root of a. That little number n is called the index. And what's underneath is still called the radicand. And if there's an index in there, if the nth root of a equals some number c, then we're going to say that a is equal to c to the n. And so we're looking at other roots. If I look at the square root, because it's the square root, we can almost think of that having an invisible index of 2. We're asking, what do we raise to the second power? But for other indices, we've got to look at it a little bit. One root that you commonly see here of is the cube root. And for a cube root, we've got an index of 3. So for example, if I take 2 to the third power, if I cube 2, 2 times 2 times 2 would give me 8. So we'll say that the cube root of 8 is 2. Instead, if I took negative 2 to the third power, well, that would be negative 2 times negative 2 times negative 2. That would give me negative 8. So I can take the cube root of a negative number. The cube root of negative 8 is negative 2. And it will turn out that if the index is odd, you can have a negative radicand. So that's one way where some of these roots are quite different from our square roots. So in order to get these, again, it's easier if you're very comfortable with your multiplication facts. If not, some people are going to go ahead and try them with trial and error. Some calculators have radicals with an index on them. You can play with yours to see if you can use it to simplify. But let's go through and let's try a couple by trial and error. If I ask for the fourth root of 81, if you were to guess what number to the fourth root do you think would give me 81? Well, hopefully everybody recognizes 81 as 9 times 9. And then 9 is 3 times 3. And so is everybody all right? Looking at that factorization, 3 to the 4th would be 81. So the 4th root of 81 is 3. What if I asked for the 5th root of 32? Can anybody think of a number that I can raise to the 5th power and get 32? A number that I can multiply by itself 5 times and have a product equal to 32. If you were a guessing person, what would you guess? Two. Let's see, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 2 to the 5th is 32, and the 5th root of 32 would then be 2. And so we start looking at other roots. And so we can add, subtract, multiply, and divide if they have the same index. And again, to add and subtract, they also have to have like radicands. Let's just look at multiplication and division. If I have the nth root of a, and I said nth root, and I didn't write it, I apologize. The nth root of a times the nth root of b, that'll be the nth root of a times b. If I have the nth root of a over the nth root of b, I get the nth root of a over b. Right now, that sort of sounds and reads like alphabet soup. Let's look at this with numbers. If I take the cube root of 7 times the cube root of 49, well, no number to the 3rd power gives me 7. No number to the 3rd power gives me 49. But does anybody notice anything about the relationship between 7 and 49? One way we could multiply them and get the cube root of 343. But another way, does anybody notice that 49 is 7 squared? So that would give me the cube root of 7 to the 3rd. And so that would just equal 7. Likewise, if I have the 4th root of 162 x to the 5th over the 4th root of 2x, because the indices are the same, I can go ahead and divide 100 and get the 4th root of 162 x to the 5th over 2x. Let's see. 2 into 162 is 81. X into x to the 5th is x to the 4th. So we can take the 4th root of 81 times the 4th root of x to the 4th. And I think we already saw that the 4th root of 81 is 3. And does it make sense? The 4th root of x to the 4th would just be x. And so we can simplify that to 3x. And we're going to go on with this idea next class. And it will take us to the ability to turn exponents into, of all things, fractions. I'm gonna call it a day here. So I'm gonna stop sharing. Maybe, if it lets me. And stop recording.